Hi everyone, this is Mrs. Raposa. On Wednesday, June 9th, some students were absent from Block 1 when we did these notes, and Block 2 was shortened because of bio-MCAS testing, so we did not get a chance to get to these notes. So I'm going to go through how to use the law of sines to solve triangles. The law of sines says that the sine of angle A is to A, the same way that the sine of angle B is to its opposite side B, as the sine of angle C is to its opposite side C. Notice that when we set this up, angle A is opposite side A, angle B is opposite side B, and angle C is opposite side C. When you use the law of sines, you typically only use two of those ratios set equal to each other, and not all three. We can also write this upside down. We can say that A is to sine of A, as side length B is to sine of B, as side length C is to sine of angle C. Remember that these denominators here and these here, these are side lengths. Side lengths here. These are angle measures that we're taking the sine of. So let's take a look at the three cases for which you use the law of sines. The three cases that we use law of sines are when you have the angle-angle-side condition, the angle-side-angle condition, or there's a special case with the side-side angle. So in these two cases, you have two angles and a side. And sometimes the two angles that you're given, like in example 1, the side length that's given is not in between the two angle measures. For case 2, you can see that we have two angles and a side, but the side length is between the two given angle measures. So for case 1, this is the angle, angle, then the side condition. And for case 2, this is the angle, side, angle condition. And in both of these cases, these are the easier ones. You'll see when you do side-side angle, it gets a little bit more involved. So for these, I can simply say, well, I want to find side length A first. Then I can say side length A is to the sine of angle A. So sine of angle A is to side length A, as the sine of angle B is to side length B. This is side length B, opposite angle B. And to set that up, sine of A would be sine of 29 degrees. Is to A over A equals sine of 85 degrees over 9. So basically I'm just solving a proportion. And when you solve a proportion, you can do it many ways. You can multiply each side by 9a if you want to, but I'm going to go ahead and just do the butterfly method since both ratios are set equal to one another. Then I'll know 9 times the sine of 29 degrees is equal to a times the sine of 85 degrees. And to solve for a, all I need to do now is just divide by sine of 85 degrees. Remember, sine of 85 degrees is just a decimal. And I can do this all in, that'll cancel. I can do that all in one sweep in the calculator. So let's take a look. Oh, there's a lot of glare on that. Sorry, let me put it over here, it's a little better. So we'll have sine, 9 times the sine of 29 degrees divided by the sine of 85 degrees. And that'll give me about 4.38. So A is about 4.38. Now to solve a triangle, I need to find all missing side lengths and all missing angle measures. So I know two angles and one side, so I need to solve for one other angle measure and two other sides. I have one of them already. To find the missing angle measure, that's pretty easy because I know all three interior angles of a triangle add up to 180. So I'm not even going to go through that because I know you know how to do that, but this would be 66 degrees because those three numbers add up to 180. Now to find side length C, I'm going to say that sine of 66 is to its opposite side length, c. Sine of 66 degrees is to c. And I can go this way if I want to because I know what this is, but I'll go it this way. Is the sine of 85 degrees is to 9. And to solve that equation, again, I can know that 9 times the sine of 66 degrees is equal to c times the sine of 85 degrees. And to solve for c, all I need to do is to divide each side by whatever the sine of 85 degrees is. And again, I'm going to go right to the calculator. And so go to the calculator and I do 9 times the sine of 66 degrees and then divide that by the sine of 85 degrees, and that gives me 8.25. So C is approximately 8.25. So then we've solved for the missing side lengths A and C, and the missing angle measure, C, you know how to find that. That's just 66 degrees. So that example is solved. Let's go to case 2 when we have the angle side angle condition. Again, I'm going to solve for these two side lengths and this missing angle measure. This missing angle measure is the easiest one to solve for, as I know that these three add up to 180, so 75 and 50 add up to 125. Subtract that from 180 degrees, and I'm going to get that the measure of angle C is equal to 55 degrees. So now let's solve for side length A, and across from angle B is side length B. So to do that, I need to start with a ratio where I have an angle measure and its opposite length both known. And this is the only case where I know both the angle measure and its opposite length. These two I don't know. All I know is the angle measure, not the opposite length. So I'm going to have to use this. Sine of 55 degrees is to its opposite length 6. Let's solve for A first, as sine of 50 degrees is to side length A. And that's an A, not a 9. So A times the sine of 55 degrees is going to equal 6 times the sine of 50 degrees. Oops, 50 degrees. And to solve for A, just divide each side by whatever the sine of 55 degrees is. And you can put that right into the calculator. I'm not going to do it with you because you know how to do that, but that'll give you the A is about 5.76. About that. So now to solve for side length B, I'm going to just do it again. Sine of 55 is to 6, as the sine of 75 degrees is to B. And that will give me 6 times the sine of 75 degrees is equal to B times the sine of 55 degrees. And to solve for B, all I need to do is divide each side by the sine of 55 degrees. And I'm not going to go through that, but if you do 6 times the 75 degrees, 6 times the sine of 75 degrees, and then divide it by the sine of 55 degrees, you'll get that B is about 7.08. Okay, after going back and looking at the directions, I realized I was supposed to round angles to the nearest tenth and lengths to the nearest to the 3 significant digits, so 3 decimal places. I went back and changed all of the lengths to round to 3 decimal places instead of 2. And the angle measures, I don't need to round to the nearest tenth because they're both whole numbers anyway. Okay, let's look at the third case for which you would use law of sines, and that's when we have 2 sides and an angle that's not between the 2 sides. If the angle was between the 2 sides, if I had a side, then an angle, and then a side, then I would know to use law of cosines to solve for the opposite side. Remember, side, side, side condition, when you have all 3 side lengths, you also use law of cosines. But you use law of sines in this case. So we don't know the length of this side, but I know that this is 10 centimeters. This should have a 30-degree angle in there. It doesn't. So in all 3 of these, you can go ahead and put a 30-degree angle. So we know an angle. We know a side, and I know the side not included in those. The other side has to be 4 centimeters. So it's 30 degrees, 10 centimeters, and 4 centimeters. Angle, side, side condition, or side, side angle if you go backwards. So what I did was I took the compass. I had the students in class in first block. We measured with a ruler from here to be 4 centimeters. We actually measured it out, adjusted the compass to be 4 centimeters. And then I had them draw an arc where the radius from this center to anywhere on this arc would be 4 centimeters. So if this side length is 4 centimeters, you can see that the triangle really wouldn't even be formed. Even if I went straight down, I still don't reach. So this has a length of 4 centimeters. And to find the measure of this angle B right here, I couldn't even do it. There is no angle B. That I cannot make a triangle with an angle measure of 30 degrees, the next side length 10, and the next side length 4 centimeters. And if I was trying to figure out what this angle measure was, I could use a law of sines, and you can see it won't even work using law of sines, because I would say, well, this is A and this is B, then this is angle B, which really isn't even there. But the sine of angle B is to 10, the same way that the sine of 30 degrees is to 4 centimeters. And the sine of 30 degrees, that's just 0.5 or 1/2. So really what I have is 10 times 1/2, or 10 times the sine of 30 degrees, 10 times 1/2, is equal to 4 times the sine of angle B. And to solve for angle B, I'd first have to get sine of B by itself, so divide each side by 4. And you can see that that would give me on this side 5/4 equals the sine of angle B. And if you try to go to the calculator to do the sine inverse of 5/4, you're going to get an error message. But that's because there is no angle measure whose sine is more than 1. This is more than 1. So the sine of any angle measure has to be between 1 and -1. So there is no angle measure whose sine is 1.25, which is 5/4. So that verifies it. Okay, so we found out that for this first example, the triangle can't exist, and the law of sines confirms that because the sine of inverse of 5/4 does not exist. So let's go on to the second case. For this case, we opened up the compass to 5 centimeters, and so we'll have a 30-degree angle, then a 10 centimeter length side, and then a 5 centimeter length side. So we opened up the compass to 5 centimeters, we measured it from this point to this point to be 5 centimeters, and drew an arc with a radius of 5 centimeters. And when we drew that out, we saw that there's only one point on this side of the triangle which a 5 centimeter side would touch, and that would be right here. And students told me that it did look like a 90-degree angle, and we actually confirmed it using the law of sines. So using the law of sines, I don't know what this angle measure is. I'll call this angle B, but the sine of angle B is to 10 centimeters, the same way that the sine of 30 degrees is to 5. And again, the sine of 30 degrees is just 1/2. So this is 1/2 times 10 is equal to 5 times the sine of angle B. And 1/2 of 10 is just 5. So we have 5 equals 5 sine B. And if you divide each side by 5, you'll end up with 1 equals sine B. So we need to know what angle measure has a sine of 1, and that's a 90-degree angle. Again, if you go to the calculator and do the sine inverse of 1, you'll get that that is a 90-degree angle, or a right angle. So the measure of angle B would be 90 degrees. And for the last case of the angle side-side condition, we let this side over here be 6 centimeters. So what we did was we set the compass to 6 centimeters, drew the arc, and as you can see, this time it touches the other side of the triangle in two different directions, in two different places, which means there's actually 2 triangles that can be formed here. One of the triangles is this triangle, triangle ABC here. And that would be an acute angle, less than 90. I could also draw, this would be 6 centimeters here. I could also draw the other side of the triangle this way. And this would be 30 degrees, 10 centimeters, and 6 centimeters. So there's another way, and that would be an obtuse angle here. So we have to find which 2 different types of triangles could be formed with a 30-degree angle, 10 centimeters, and then 6 centimeters side. So to do that, we're going to say the sine of this, let's do this one first. The sine of this angle is to 10. Sine of angle B is to 10, as the sine of 30 degrees is to 6. Now whether I'm solving for the acute angle or the obtuse angle, I still have to set the same ratio up. Sine of angle B is to 10 as sine of 30 is to 6, or sine of angle B is to 10 as sine of 30 is to 6 on this triangle. So you're just looking at 2 different triangles. Either way, I'm going to have 6 times the sine of angle B equals 10 times the sine of 30, which is 10 times 1/2. So that'll give me the sine of angle B is equal to 5/6. And to find out what angle measure has that sine value, I do the sine inverse of 5/6. And if you do the sine inverse of 5/6, you will get 56.4 degrees. So the measure of angle B could be 56.4 degrees. That's if I have this triangle right here. A is 30 degrees, B is 56.4 degrees, and this would be 10 centimeters. And I could find the other length by doing sine of 30, excuse me, this is 6 centimeters. I could find the other length by finding this angle measure right here, adding these 2 together, subtracting from 180, and saying the sine of 30 is to 6 as the sine of this angle is to this side. You'll see you get a different length on this one than if you do the obtuse triangle. So the obtuse triangle looks more like this. And we know that this is 30 degrees, this is 10, and this is 6. To find this obtuse angle, I'm going to have to subtract this angle measure, 56.4, from 180. That's because there's 2 angle measures that have a sine of 5/6. One angle measure is 56.4. The sine is y over r, so 5/6. But there's also another angle measure here between 90 and 180 that also has a sine of y over r is 5/6. And to get this angle measure that goes from here to here, I just do 180 degrees minus 56.4 degrees. And that would give me a 93.6 degree angle. So this is another possibility, which means that I'm going to have a different side length on this triangle than I would on this one. This side would be a little longer. So there's 2 different triangles that can be formed.